the map of everything, from ancient star charts to GPS and the cosmic web. Welcome or welcome back to Asleep in Class, where we turn quiet lectures into restful journeys through history, science, invention, and the wider world. Here, curiosity can slow down, the day can loosen its grip, and there's no test waiting at the end. Tonight, the classroom opens into the long human effort to map everything. A map begins as a way to answer a simple question: where are we? But the answer never stays simple for long. To know a place is also to ask what surrounds it, how far it reaches, who can cross it, who can claim it, and what waits beyond its edge. Across time, maps have helped people move through darkness, sail beyond familiar coasts, divide land into records, and turn distant worlds into reachable surfaces. They have guided return journeys and opened dangerous routes. They have protected lives, supported power, revealed hidden patterns, and sometimes made the world look simpler than it really is. The need to map everything is partly practical and partly restless. Human beings keep turning space into pattern, not because one map can hold the whole truth, but because each map pushes the edge of the known a little farther away. The story begins where many maps began, under the night sky. The first maps were in the sky. Before people tried to draw the whole earth, they already knew that place had pattern. Long before written history, hunters and herders followed ridgelines, water, stars, winds, and the shape of the horizon. Near the sea, travelers learned how water, weather, and distance reshaped the edge of land, while farming communities watched the ground until season, direction, and memory became part of the same knowledge. Some of that knowledge stayed in movement. Some was fixed into stone, path, mound, temple, or monument. In Egypt, during the 3rd millennium BCE, certain pyramids and sacred buildings showed how direction, sky, and geography could be bound into architecture, so that land itself became part of a larger order. The sky became the widest guide of all. A farmer waiting for the right season watched familiar stars return before preparing a field, while a sailor leaving harbor kept his course by lights that rose and set with dependable order. When paths faded in darkness, a traveler far from home could still look upward. The sky did not belong to one road, village, or kingdom. It stretched over all of them, giving human memory a structure larger than the nearest landmark. The earliest maps were often carried before they were drawn. Star patterns could survive inside stories, while lunar cycles moved through songs. A doorway or temple wall could hold a sunrise point. Across generations, people learned that the heavens followed patterns. The moon changed its face, disappeared, returned, and divided the month into visible stages. As the sun shifted its path through the year, daylight lengthened, shadows changed, and solstices or equinoxes marked the turning points. Communities tied those patterns to fieldwork and fishing, to travel and worship, to markets and public duties. Sky knowledge became a working calendar. That kind of mapping did not separate the practical from the sacred as neatly as modern people often do. A temple alignment could honor a god and preserve an observation at the same time. A seasonal festival could carry religious meaning while reminding a farming village that labor was changing. A star story could teach children the shape of the night while keeping older memory alive. Maps began in that overlap where survival, ceremony, and repeated attention met. Early pictures of the world grew from the same search for order. Many cultures described a broad land beneath the sky, waters near the edge of the known world, sacred mountains, heavenly domes, underworld regions, or divine boundaries beyond ordinary travel. Some traditions treated the world as flat or enclosed, which made sense from the ground. A person standing in a field sees the horizon as a line. A village learns nearby rivers before it learns the planet. A trader trusts the road that has carried caravans before. These models tried to organize a world that no one could yet see whole. Observation, however, kept pushing beyond the local view. Travelers who moved north or south found that the night sky changed, with some stars climbing higher while others sank lower or vanished below the horizon. Sailors noticed that a distant ship did not return to sight all at once. Its mast appeared before its hull. During a lunar eclipse, Earth laid a curved shadow across the moon. In different places, upright objects cast different shadows at the same time of day. By classical antiquity, observations like these had become arguments for a spherical Earth. The idea of a curved Earth did not sweep through daily life in a single moment. Farmers still judged soil, rain, frost, and daylight by local experience. Sailors still needed winds, currents, landmarks, and safe harbors. Travelers still cared about wells, roads, mountain passes, and danger along the way. Yet the larger frame changed. Earth could be treated as a body with form, not merely as the ground that happened to hold each town. Once that happened, map-making inherited a harder task. It had to connect places no single person could see together. A local route could remain simple in memory. Leave the gate, follow the river, cross near the old stones, and turn toward the sea. A sky pattern could guide movement without ever becoming a drawing. A curved world demanded another level of trust. Direction, distance, horizon, and position had to be joined through travel reports, shadow measurements, star positions, and shared calculation. A map now had to hold what people saw and what careful reasoning revealed beyond sight. That change began the long expansion of human mapping. People mapped to plant at the right time, sail beyond familiar water, carry memory across generations, place home within a larger order, and press against the edge of the unknown. The first maps helped people find time, direction, and return. They also opened the next question. If the sky could reveal order, and if shadows and horizons could reveal the shape of Earth, then the world itself could be measured. Earth becomes measurable. Once the world could be treated as measurable, maps changed their purpose. They no longer had to preserve only a remembered landscape, a sacred order, or a route between familiar places. Instead, a map could begin to make a claim. Rivers, cities, distances, and routes belonged inside a larger argument about the shape of Earth itself. Among the oldest surviving world maps is one from Mesopotamia. The Babylonian map of the world, often called the Imago Mundi, was carved into a clay tablet, most likely in the late 8th or 7th century before the Common Era. Its world centered on Babylon and the Euphrates, with surrounding regions and a circular ocean or bitter river near the edge. It was not a modern geographic survey, and it was not trying to be one. It joined real places, political memory, mythic distance, and learned tradition into a single, ordered picture. The world people knew had become something that could be held in the hand. Yet, a hand-sized world raised larger questions. If Earth curved beneath human feet, then a true map could not stop at local rivers and surrounding lands. Greek thinkers pushed those questions into geometry. By the 4th century BCE, Aristotle gathered arguments for a spherical Earth, including the curved shadow Earth cast during lunar eclipses and the way different stars appeared from different regions. Earth had form, and that form could be reasoned from observation. Eratosthenes carried the question from shape to size. Around the 3rd century BCE, working in Alexandria, he used sunlight, shadow, distance, and geometry to estimate Earth's circumference. At Sin, near modern Aswan, the sun was reported to shine nearly straight down at noon near the summer solstice. Farther north in Alexandria, a vertical object still cast a shadow at the same time. Treating the difference as an angle on a spherical Earth, Eratosthenes used the distance between the two places to calculate the size of the whole. The result was not perfect by modern measurement, but the method was extraordinary. He measured a planet without leaving it. Measurement changed what a map could ask from the world. A road description could guide a traveler toward the next town, and a sea chart could help a sailor follow familiar waters. A measured Earth, however, demanded relationships among places no traveler could see together. Distance, direction, angle, and position became part of the mapmaker's craft. The world was no longer only a surface to cross. It was a body that could be divided, compared, and calculated. Ptolemy carried that mathematical habit into a system that later mapmakers would inherit. In the 2nd century CE, his geography organized places through latitude and longitude, giving mapmaking a coordinate language. A place could now be described not only by story, road, ruler, or river, but by position within a wider grid. Many of Ptolemy's locations were wrong by modern standards, and the known world in his system remained limited. Still, the idea was powerful. A map could become a framework for placing every known location in relation to every other one. That framework created one of cartography's permanent problems. Earth is curved, but most useful maps are flat. A globe can preserve the rounded form more faithfully, yet it is awkward to carry, hard to copy, and limited in detail. A flat map can sit on a table, hang on a wall, travel in a book, or serve a navigator, but it must distort something. Shape, size, distance, direction, or area will suffer. Projection is the art of choosing which truth to preserve and which truth to bend. That problem never disappeared. Every world map carries a compromise inside it, even when the compromise is hidden by familiar lines and colors. A map that helps a sailor may exaggerate the size of northern lands, while a map that protects area may bend shapes until countries look strange. Even a classroom wall map can seem neutral, while quietly teaching one version of scale, center, and importance. The more humans tried to map everything, the more clearly they faced a paradox. The world could be measured, but no single flat picture could hold it without loss. Still, this new precision gave mapmaking its next great power. The world could be too large for one person's sight, and still not be beyond human reasoning. Shadows in two cities could reach toward the size of Earth, while stars helped locate latitude and coordinates, gave places numerical addresses. Clay, parchment, and later paper could carry calculation as well as memory. Once Earth became measurable, maps could do more than describe where people had been. They could point toward places not yet reached, estimate distances not yet traveled, and prepare the way for maps that would serve pilgrims, merchants, sailors, rulers, and empires. Maps for routes, faith, trade, and power. Once maps measured the world, they also had to serve people moving through it. A coordinate placed a city inside a wider grid, but movement required more than position. A traveler looked for the road ahead, a place to rest, and trust that the route would hold. Merchants depended on reliable passages for goods. Pilgrims followed paths that joined distance to devotion, and sailors worked from recognizable waters, usable bearings, and warnings before danger. Mapmaking grew because travel kept asking for more than theory. Some route knowledge stayed close to the ground. Roads tied settlements to markets, farms to river landings, and forts to the systems that supplied them. In the Roman world, travelers counted routes by milestones and distances between towns. A person did not require a perfect picture of Earth to cross a province. The next road and the next stop mattered more. Even a schematic route map organized travel by sequence. Sometimes the map's value lived not in shape, but in order, from here to there, then onward again. Faith gave mapping another purpose. Pilgrimage routes turned geography into spiritual passage, and sacred maps placed holy sites inside a meaningful world. A road to a shrine was never only a road. It carried danger and prayer, the need for inns, and the memory of others who had walked before. In medieval Christian, Islamic, Buddhist, Hindu, and other traditions, sacred geography connected distant places to belief. Some maps cared less about exact scale than about direction, destination, and meaning. Trade asked for precision of another kind. Merchants required routes from ports to river mouths, over mountain passes, through caravan towns, and across desert roads toward markets. Goods carried languages and technologies with them. Disease, money, rumor, and political claims often followed the same routes. A map helped a ruler see tax routes, a merchant weigh risk, or a shipmaster plan a voyage. As trade networks widened, geography became practical intelligence. Route knowledge moved goods. Route control shaped wealth. At sea, usefulness often mattered more than elegance. Portolan charts, which appeared around the Mediterranean in the later Middle Ages, gave sailors shore profiles and harbor names, then covered the sea with compass roses and bearing lines. They did not solve every problem of global geography, but they helped mariners move from port to port with confidence. A chart like that belonged to work. It lay open near a navigator's hand, where water, direction, and experience met. The sailor needed landmarks he could recognize, and a bearing he could follow. Other mapping traditions developed their own strengths. Islamic geographers preserved, corrected, and expanded inherited knowledge, while linking scholarship to travel, trade, astronomy, and administration. Chinese mapmakers built records for administration and war, for rivers, harbors, and frontier rule across long periods of imperial government. Mapmakers worked for different institutions, but the pressure remained familiar. Authority had to fit onto land, settlements had to connect through water, and movement had to pass through controlled space. As maps became easier to copy, their power widened. Manuscript maps could be rare and slow to reproduce. Printing changed that. Maps moved through workshops and booksellers, then into schools, ports, courts, and merchant houses. Mistakes could spread, but so could discoveries and corrections. By the 16th century, printed atlases were turning regional and sea maps into ordered books of the world. The atlas became portable because it trained readers to think of the world as something assembled. That assembly was never neutral. For a ruler, a map turned land into countable territory and roads into military corridors. Distant provinces looked more governable once they could be drawn and named. Merchants found opportunity in maps, while pilgrims used them to order journeys through sacred space. Sailors carried them through dangerous waters. In one set of hands, a map supported a tax claim. In another, it blessed a pilgrimage, prepared an invasion, or preserved memory. By the time printed maps and atlases spread, inherited world pictures were crowded with roots. The next rupture would come when ocean crossings forced inherited maps to make room for continents and consequences they had not been built to hold. The world map breaks open. By the time printed maps and atlases spread, inherited world pictures were already crowded with roots and claims from travelers' reports. Yet many still carried old assumptions about distance, coastlines, continents, and oceans. The world had been measured in theory, crossed in parts, and arranged in books, but it had not been forced into a truly global shape. That pressure came from ocean crossings, where ships carried ambition and error alongside violence and discovery across waters no mapmaker fully understood. Christopher Columbus belongs to this rupture, but not in the simple way often repeated. He did not prove that Earth was round. Educated European mapmakers and scholars already knew the world was spherical. The problem was not Earth's shape, but its scale and the unknown geography between Europe and Asia. Columbus believed the westward route to Asia was far shorter than it truly was. When he crossed the Atlantic in 1492, he reached Caribbean islands, not the Indies he thought he had found. The voyage changed maps, but it also began catastrophe for many indigenous peoples whose worlds were already ancient, ordered, and fully lived before European arrival. Maps struggled to absorb what the crossings revealed. Coastlines appeared where older geography had left expectation, rumor, or blank space. Islands entered European charts with names, claims, and errors attached. Rivers and harbors became entry points for trade, conquest, mission work, and extraction. The map was no longer only a record of where ships had gone. It became a claim about what might be taken, converted, taxed, renamed, or ruled. A harder question followed the ships. What did it mean to draw lands that other people already knew as home? Amerigo Vespucci helped shift the interpretation of those Atlantic lands. The issue was not simply who arrived first or whose name endured. Vespucci argued that the lands across the ocean were not Asia's outer edge, but part of a separate continent or New World. In 1507, Martin Waldseemüller's printed world map used the name America, drawing from Amerigo's name, and placed that idea before readers in visual form. A name on a map could travel faster than correction. Once printed, copied, studied, and repeated, it could help make a new geography feel settled. Ferdinand Magellan's expedition pushed the rupture further. In 1519, the fleet sailed west from Spain, seeking a passage through the Americas toward Asia. The voyage found the strait at the southern end of South America, crossed the vast Pacific, and revealed how badly many earlier estimates had understated the ocean's scale. Magellan died in the Philippines in 1521, so he did not personally complete the first circumnavigation. One surviving ship, the Victoria, returned to Spain in 1522 under Juan Sebastián Elcano. The expedition proved through passage what geometry had already argued. Earth could be encircled by sea. That proof carried a terrible weight. The expanding map did not spread as a neutral sheet of knowledge. It helped organize empire. New routes moved silver and sugar, spices and timber, weapons and administrators, missionaries and soldiers, and enslaved people forced into expanding imperial systems. As crops crossed oceans, daily diets changed far from the fields where those plants had first been grown. American foods such as potatoes, maize, tomatoes, and cacao entered lives across the Atlantic world and beyond. America's horses, cattle, wheat, and new forms of land use reshaped regions already under pressure from conquest and disease. Violence, forced labor, and displacement destroyed communities while remaking whole regions. The same map could therefore mean very different things depending on whose hands held it. To a European monarch, a new coastline might look like territory or revenue. To a merchant, it might show a route to profit. To a sailor, it might mark danger, wind, water, and survival. To indigenous people, the lines arriving from across the sea could become instruments of invasion, seizure, forced conversion, and loss. A map could connect the world while also helping divide it. Mapmakers faced a practical crisis as well as a moral one. Reports arrived from voyages that disagreed with older authorities, and islands appeared in the wrong places. With better measurement, coastlines stretched, broke, vanished, and reappeared. The Americas forced Europe, Africa, and Asia into a different relationship on the page. Oceans widened. Trade winds and currents gained new importance, and harbors became strategic points in a world whose scale could no longer be ignored. By the end of these voyages, the map of the world had become more connected and more unstable at the same time. It held new continents, larger oceans, wider routes, and sharper claims. It also carried the consequences of contact, exchange and extraction, curiosity and violence, naming and erasure. The human need to map everything had entered a harsher phase. The next challenge would be precision, not only reaching distant shores, but knowing exactly where a ship stood on the open ocean. Longitude, Mercator, Harrison, and the ocean grid. After ocean crossings broke open the world map, the next problem was not simply reaching distant shores. Ships had to know where they were while the shore was gone. On open water, a vessel might travel for weeks with no landmark, no road, no tower, and no fixed point except the sky. Captain could know that Earth was round, that oceans connected, and that charts showed routes between continents, yet still face a dangerous question each day. Where does this ship stand now? Latitude offered the easier half of the answer. Sailors used the height of the sun at noon, or the altitude of familiar stars, to estimate position north or south. The method required skill, instruments, and correction for weather, but it rested on a visible relationship between the sky and Earth. Longitude was different. East and west position depended on time. Earth turns through 360 degrees in a day, so every hour of difference equals 15 degrees of longitude. To find longitude at sea, a navigator had to compare time at a fixed reference point with local time aboard ship. Before that comparison became reliable, sailors worked with imperfect methods. Dead reckoning estimated position from speed, direction, and elapsed time, but small errors accumulated across long distances. Lunar distance methods used the moon's position against the stars. Though they demanded clear skies, accurate tables, and careful observation, a ship could cross an ocean and still be uncertain about how far east or west it had drifted. In bad weather, near hidden reefs, or close to unfamiliar coasts, that uncertainty could turn lethal. Maps and projections tried to help. Gerardus Mercator's 1569 world map became famous because it served navigation. On his projection, lines of constant compass bearing, called rum lines, appeared as straight paths. That was useful for sailors who needed workable courses more than a perfect picture of land size. The cost was distortion. Lands near the poles grew far larger than they were, and the world's proportions bent around the needs of navigation. Mercator showed a recurring truth of map-making. A useful map often sacrifices one kind of accuracy to preserve another. Still, projection alone could not solve longitude. The missing tool was reliable time. John Harrison entered that problem from outside the usual centers of academic science. Born in 1693, he was a self-taught English clockmaker and former carpenter, and he understood that a clock at sea had to survive motion, salt air, changing temperature, and long voyages without losing its discipline. A land clock could sit still. A sea clock had to keep faith with time while the ship pitched, rolled, and crossed climates. Harrison spent decades building marine timekeepers. His early machines were large and ingenious, made to resist the forces that ruined ordinary clocks at sea. Later, his smaller H4 watch became the great breakthrough. It looked more like an oversized pocket watch than a traditional sea clock, yet it kept time with remarkable accuracy during trial voyages. With a dependable timekeeper, A navigator could compare local noon aboard ship to reference time carried from home. The difference revealed longitude. Time became location. The change reached beyond one inventor. Accurate marine chronometers helped turn ocean navigation into a more dependable practice. A captain still needed charts, skill, and weather judgment. But the open sea no longer had to be guessed through dead reckoning alone. Cargo moved with less uncertainty, and naval orders traveled through more predictable routes. Migration and insurance, trade and empire, all operated with more confidence when ships knew their positions better. The map became stronger because the clock had joined it. This was another stage in the human effort to map everything. The ocean had once seemed like a wide blank between coasts, broken by islands, and remembered through winds, currents, and hard experience. With projections, tables, instruments, chronometers, and repeated voyages, that blank began to fill with measurable position. Numbers placed a ship on the globe, even when no land appeared in sight. The sea became less like an empty space outside the map, and more like a grid that people could cross, calculate, insure, patrol, and claim. Yet precision brought its own pressure. Better navigation did not make ocean travel harmless, and it did not make global power innocent. The same tools that protected sailors also strengthened navies, merchants, colonizers, and empires. A more accurate map could save a ship from wreck. It could also guide a fleet toward war, extraction, or rule. The need to know exactly where a ship stood on the open ocean led naturally into a larger ambition. If the sea could be measured, then land could be surveyed with even greater force, turning roads, borders, property, and states into mapped systems. Maps become infrastructure. If navigators had learned to measure the sea, surveyors pressed measurement into land with even greater force. Roads pulled settlements together, borders separated jurisdictions, property lines turned land into legal record, and canals or railways demanded planned corridors across terrain. The question was no longer only how to reach a coast or cross an ocean. It became how to define land, divide it, tax it, defend it, improve it, sell it, and govern it. Surveyors gave that ambition a working method. Through triangulation, they measured one baseline carefully, then used angles to build larger networks of position across fields, hills, rivers, and towns. Memory, custom, boundary stones, and local agreement had once shaped how communities understood land. Surveyors turned those older understandings into lines on paper, and those lines entered deeds, tax records, military plans, road projects, and court disputes. A map did not merely describe land. It helped decide what land legally was. As surveying expanded, mapmakers also had to face Earth's real shape. A simple sphere was useful, but Earth is not a perfect sphere. It bulges slightly at the equator, flattens near the poles, and varies in smaller ways across mountains, valleys, and ocean basins. Geodesists turned that difficulty into a science of measurement. They asked how to measure Earth itself well enough that local surveys could fit into larger systems. Standardized coordinates and datums gave measurements a shared reference, letting one map agree with another instead of floating inside its own private version of space. Topographic mapping added another layer. Roads, canals, railways, forts, farms, and towns all met the same problem. Land rose, fell, drained, flooded, and blocked movement. Elevation changed cost, speed, danger, and possibility. A line across a map might look simple until it met a mountain grade or a river valley. Contour lines, shaded relief, and measured heights let map users see the shape of the land before they tried to cross or build on it. Terrain became something planners could study before boots, wheels, rails, or armies arrived. Property mapping carried different consequences. Cadastral surveys turned landholding into mapped record. Memory, neighbors, trees, stones, streams, and older custom had once carried boundary knowledge from one generation to another. Surveyors tied those boundaries to documents and authority. That work settled some disputes and created others. A map might clarify ownership for one person while erasing another person's older claim. In colonial settings, mapped boundaries often turned indigenous homelands into parcels, concessions, districts, or resources for outside powers. States also learned to think through maps. Governments marked provinces, planned roads, routed canals, placed railways, organized mail, counted farms, tracked populations, and moved troops through mapped systems. Armies read bridges, passes, elevations, and supply lines as survival problems. Engineers measured slopes and rivers before committing labor and material. Administrators turned districts, addresses, roads, and records into routines of government. As map-making entered public offices, it became a hidden skeleton for decisions that seemed ordinary once they reached the ground. Map makers widened the habit further with thematic maps. Instead of showing only roads, rivers, borders, and towns, maps began to show patterns that no one could see all at once from any hilltop. In 1854 London, John Snow traced cholera deaths through streets elsewhere. Officials shaded population across districts, and geologists linked rock layers to mines and building materials. Map makers also placed weather, crops, poverty, voting, risk, and public health onto maps. The map became a way to see invisible relationships, not only visible places. That power made maps useful and dangerous at the same time. Maps revealed floodplains before towns expanded into danger, helped railroads choose grades, guided farmers toward drainage problems, and warned armies away from bad roads. The same authority also hid inconvenient people, renamed places, exaggerated control, classified land for extraction, and pressed complex communities into simple administrative shapes. The more official a map appeared, the easier it became to mistake its lines for the whole truth. By the modern age, land maps quietly shaped ordinary life, even when no one noticed them. Addresses guided mail and emergency response. School districts, voting districts, utility corridors, zoning boundaries, property deeds, roads, and tax parcels all depended on mapped systems. The map had moved from parchment and atlas pages into law, infrastructure, and bureaucracy. It no longer only helped people travel through the world, it helped build the world they traveled through. From there, the next transformation would come when people began to look down on Earth from above. from aerial view to digital Earth. After maps became infrastructure, height changed the mapmaker's view. For most of history, people mapped land from the ground. They climbed towers and hills, worked from ships near shore, and carried measurements across terrain. Then, balloons lifted observers above streets and fields. Aircraft carried cameras over battle lines. Rockets and satellites eventually raised the view until Earth itself entered the frame. A road, river, city, battlefield, forest, or coastline no longer had to be pieced together only from movement across it. Seen from above, land turned into pattern. The first elevated views did not instantly create a digital planet, but they changed expectation. Balloon observers and early aerial photographers showed streets, fortifications, farms, and rivers spread across a surface. During war, aircraft made overhead mapping urgent, and reconnaissance photographs helped armies read trenches, roads, bridges, rail lines, supply routes, and troop positions. Aerial images turned terrain into evidence. What a patrol missed on the ground, a camera above the field might catch in one frame. Satellites widened that view until Earth itself became the subject. Weather satellites made storms visible as vast systems rather than local surprises. From orbit, remote sensing let scientists and governments watch forests and deserts, ice and crops, coasts and cities, fires and floods. In 1972, Landsat-1 began a long record of Earth observation, giving researchers repeated views of the same changing planet. A map no longer froze one moment. It returned as measurement over time. Those measurements entered ordinary life quietly. Weather maps moved through television broadcasts, newspapers, phones, and public routines. Farmers read aerial and satellite information for crop stress, drainage, drought, and disease pressure. Emergency planners followed hurricanes, wildfires, floods, evacuation routes, and search areas through maps that changed with events. Environmental scientists tracked deforestation, shrinking ice, urban growth, and damaged coastlines. A map no longer only helped someone find a road. It helped society watch a living planet. Digital mapping added another layer. Geographic information systems, often shortened to GIS in technical settings, turned maps into databases. Instead of one paper sheet carrying one kind of information, map makers and analysts stacked roads over property lines, population over flood risk, pipelines over soil, and hospital access over neighborhood boundaries. Planners and insurers asked spatial questions through data. So did utilities, health departments, environmental groups, police agencies, and businesses. Where is the risk? Who is nearby? What changed? Which route, district, building, or field needs attention first? Satellite positioning turned that digital Earth into personal navigation. The global positioning system depended on satellites, atomic clocks, radio signals, and precise models of Earth. A receiver compared signals from multiple satellites to calculate position, turning the globe into an invisible coordinate machine. The system grew from military and scientific needs, then entered civilian life so thoroughly that many people stopped thinking of it as extraordinary. Once a phone located itself on Earth, the map no longer waited to be unfolded. It followed the user. That shift altered ordinary movement almost overnight. For decades, families spread folded maps across tables, highlighted routes, asked for gas station directions, and packed thick road atlases. A passenger might serve as navigator, watching exits and street signs, while the driver stayed with the road. Early internet directions let people print turn-by-turn routes before leaving home, though a missed turn still threatened the plan. Dashboard units from companies such as Garmin brought spoken guidance into cars. Then smartphones absorbed the map, the compass, the traffic report, the business directory, and the blue dot into one small screen. Entire jobs changed with it. Taxi drivers once worked from memorized streets, radio dispatchers, landmarks, and hard-earned local knowledge. Pizza shops and delivery businesses used wall maps, paper tickets, neighborhood zones, and drivers who knew the back entrances of apartment complexes. With GPS and Live digital maps, delivery drivers, rideshare workers, truckers, couriers, hikers, tourists, and emergency responders gained route guidance that recalculated in motion. Arrival times turned into promises. Traffic turned into a condition the map sensed, predicted, and routed around. Convenience carried a trade-off. Digital maps saved time, reduced confusion, and opened unfamiliar places. But they also trained people to trust the blue dot more than their own route memory. Bad data sent drivers toward closed roads, private driveways, or dangerous shortcuts. Dead batteries, weak signals, outages, and poor map updates revealed how much confidence had moved into invisible systems. Location sharing helped friends meet and families coordinate, while the same location trails raised questions about tracking, surveillance, and who owned the record of movement. By the early 21st century, the road atlas had changed status. It once belonged in glove compartments, gas stations, classrooms, and kitchen tables before long trips. Later, it often became a backup, a teaching object, a collector's item, or a piece of nostalgia. Maps had not disappeared. They had grown more constant. They watched weather, guided commutes, routed deliveries, measured risk, and followed people through the day. From above and from orbit, from databases and pocket screens, Earth had become a digital surface. The next step would carry mapping beyond daily life, into hidden Earth, other worlds, and the largest structures humans have ever tried to chart. Mapping hidden Earth, other worlds, and the cosmic web. After maps entered pockets and screens, the old impulse did not stop at daily life. It reached toward places harder to stand on, harder to reach, or too large to see from any single point. Some of those places were hidden beneath Earth's own oceans. Mapmakers had charted coastlines for centuries, but the seafloor remained a different problem. Dark, deep, pressured, and unreachable to ordinary sight. Sounding lines, sonar, satellites, and research ships slowly gave depth a shape. Bathymetry revealed that the ocean floor was not a smooth basin beneath the waves. It held mountain ranges, trenches, plains, ridges, volcanoes, and fracture zones. Those hidden forms mattered for navigation, submarine cables, naval movement, tsunami modeling, earthquake science, and plate tectonics. There is a strange humility in that fact. human beings mapped the moon in extraordinary detail, while much of Earth's seafloor still demanded better measurement. The map of everything had shadows at home. Beyond Earth, mapping turned into a requirement before arrival. After Galileo turned a telescope toward the moon in 1609, its surface began to look less like a perfect heavenly disk and more like terrain. Later lunar observers charted craters, maria, mountains, and bright rays across its near side. Photography sharpened lunar maps, and the Apollo era made them mission tools. Mission planners studied terrain and sunlight, checked slopes and rock fields, protected communication paths, and weighed scientific promise before choosing where astronauts could land. A silver disk in the sky became a surface where human footsteps required planning. Modern lunar orbiters, including the Lunar Reconnaissance Orbiter, pushed that work further. Instruments measured elevation, temperature, mineral signs, shadowed craters, and possible ice-bearing regions. The moon no longer stood only as a symbol or destination, but as a mapped environment with hazards, resources, and routes. A map turned distance into procedure. Before a lander descended or a rover moved, someone had already studied the ground from above. Mars followed a similar path, though with its own long history of error and correction. Early telescopic observers drew dark markings and bright regions, trying to organize a world blurred by distance and atmosphere. Later spacecraft changed the scale of knowledge. Mariner and Viking missions sent back close views. Mars Global Surveyor, Mars Reconnaissance Orbiter, and other missions turned valleys and volcanoes, polar deposits and dust, mineral clues and elevation, data into a working geography that also carried possible traces of ancient water. Those maps let scientists read Mars as a planet with climate history, landing hazards, and routes a machine might cross. The red point in the sky had turned into terrain. By the time Mars Pathfinder and the small Sojourner rover reached the surface in 1997, Martian mapping had entered practical route planning. Slopes shaped movement, rocks threatened wheels, and dust changed sunlight. Craters, ridges, and clay-rich layers shaped a route into a scientific plan. A rover's path unfolded like a machine road trip through another world, shaped by hazard, curiosity, power, and time. On Mars, a map had to show position, safe passage, and the scientific questions waiting in the ground. By this point, the word map had stretched beyond ordinary geography. Some modern maps describe no place where anyone can stand. The same habit also turns inward, toward the body, ancestry, and identity. Genetic maps helped researchers locate genes along chromosomes, while the Human Genome Project turned human DNA into a reference sequence at the beginning of the 21st century. Later, consumer ancestry tests arranged fragments of inheritance into family trees, migration stories, and questions of belonging. Instead of roads or coastlines, these maps trace patterns inside what once seemed unreadable, asking where a life fits inside a larger history. After turning inward, the scale widened again. Long before spacecraft, star catalogs gave order to the night by recording positions and brightness. Modern surveys deepened that habit until astronomers studied the Milky Way itself as structure. Stars moving through a disk, a central bulge, dark lanes of dust, and a surrounding halo. Telescopes and space observatories changed the sky from a ceiling of lights into a measured field of distances, motions, spectra, and ages. Galaxy surveys pushed the map outward. Since 2000, the Sloan Digital Sky Survey has measured positions and redshifts for enormous numbers of galaxies and quasars, helping astronomers build three-dimensional maps of large-scale structure. Those maps show galaxies gathered along filaments, clusters, and enormous voids, forming the cosmic web across deep space. The James Webb Space Telescope pushed the time horizon farther back. In the JADES survey, the galaxy JADES GSZ140 appeared as it was about 290 million years after the Big Bang, when the universe was still young enough that early galaxies challenge ordinary expectations. Other maps looked farther back still. NASA's WMAP mission and the European Space Agency's Planck mission mapped tiny variations in the cosmic microwave background. That ancient light was released when the universe was only about 380,000 years old, after it had cooled enough for light to travel freely. These maps do not show roads, coastlines, or planets. They show structure, age, expansion, and origin at the largest scale humans can currently measure. That opportunity may not last forever. If cosmic expansion continues to accelerate, distant galaxies may one day slip so far beyond reach that their light no longer carries evidence of them to any future observer. The thought also humbles the present map. If horizons can close in the future, then some parts of reality may already lie beyond any signal that could ever reach us. Mapping the universe now is not only an act of our unquenchable curiosity, it is a rare chance for us to discover as much of the cosmos as this moment in history allows. The need to map everything began with the oldest questions of place. Where are we? What surrounds us? And how do we find our way back? It moved first through sky and shadow, then through oceans, survey lines, satellites, and pocket screens. It reached toward distant galaxies and the first light of the young universe. It also turned inward, toward the code carried in human bodies, where ancestry and inheritance became another kind of pattern. It has not ended with a final border. It has, for now, come to rest with a sharper understanding that every map carries knowledge and choice together. A map is never the whole world. In one hand, it can guide a traveler or reveal a danger. In another, it can support power, hide people, or make complicated lives look simple from far away. The older question remains beneath all of it. When human beings draw the world, what do they learn? What do they miss? And what do they change by drawing? For now, that older uncertainty can rest. The roads can empty. The oceans can darken. The satellites can pass silently overhead. The genomes and galaxies, even the far-gone galaxies of the future, can pull back to the quiet of here and now. If you are still awake, another quiet lesson will be waiting when you are ready. And if sleep has already found you, you are welcome to stay here, soundly asleep in class.